This is the walkthrough video for PCTC 2024-2025, round 2, question 10, line them up. Okay, so this is actually a very difficult question because we're given a list of coordinates for stars, and our goal is to essentially find a straight line, any straight line, that connects as many stars together as possible. And the one thing that kind of makes this question particularly difficult, especially compared to previous year's questions that are similar, is that that line doesn't have to pass through the origin, right? It just has to be any line in this map of stars that passes through as many of the stars as possible, and that's what makes it difficult. But the approach we're going to use today, or I'm going to use, is we're going to essentially identify an anchor star. And an anchor star is a star that represents a line going through it. So say this is the anchor star. Well, our line has to pass through that star no matter what. That's what we're defining the anchor star to be. Just a star where the line passes through. And we also have a slope. The slope is, of course, has an x part and a y part. The x component and the y component, because it goes up / down and it goes left / right. So line can essentially be defined by the anchor point and a given slope, right? It's almost like you may have done in maths. You have like y equals mx plus c, where c is your anchor point and m is your slope. So we're doing a very similar thing. Not exactly the same, but similar concept. So we're defining every line by an anchor point and a slope. So how's that going to help us? Well, we're going to essentially brute force this, and we can brute force it because n will only go up to 50. So there's a maximum of 50 stars. So our solution will have a maximum of 50 times 50 runs, which is like 2500. And this number seems big, but computers are so fast that our code will still run within like 100 milliseconds anyway. So brute force is fine, and we're not going to bother optimizing it too much, but I will point out in the solution where some optimizations could be made. Anyway, so what we're going to do is we're going to go through each of our input stars. So in this case, there are 6 stars. We're going to go through each of our 6 stars, assume that's the anchor star. Then we're going to go through each of the other 5 stars, and then try and calculate the slope between our anchor star and that extra star that we've just gone through. And that's going to be our slope. And we're essentially going to add that to a dictionary. And we're going to do that for every anchor point and every other star. And that will essentially give us a dictionary where the key of each item is the anchor and the slope, and the value of each item is the amount of stars that are exist on that line of given the anchor and the slope. Because remember, the anchor and the slope define a very specific line. So given that specific line, we will count how many stars lie in that specific line, and we will just kind of brute force this. Now, a question you may have is, well, the slope may differ, or the slope value we calculate may differ, right? Because, for example, if we take a look at 1, 4. So what is the slope value between 1, 4 and 2, 5? Well, the slope is x changes by 1 and y changes by 1. So the x slope is 1 and the y slope is 1. The change in x and the change in y are both 1. Okay, great. So 1, 4 is still our anchor point. Now what about 1, 4 compared to 3, 6? Well, the slope there is now 2, 2. It's not 1, 1, it's 2, 2. So how are we going to correlate that 2, 2 to the 1, 1? Because they clearly lie in the same line, right? Like the answer says they lie in the same line, and they just lie in the same line. So how are we going to ensure that even if our star is really far away and another star is really close to our anchor star, how can we ensure that those 2 stars are different distances from our anchor star? How can we ensure that we have the same slope saved for both of them? Well, the solution is, and we'll come across this later on, and it should be a bit more clearer when we code this up, but we're going to try and compress that slope down as much as possible. So here, the slope is 2, 2 relative to the anchor point, and here the slope is 1, 1 relative to the anchor point. Well, 2, 2, we can compress that down to 1, 1. 2, 2 is the same slope as 1, 1. And that's obviously the same slope as this. So now both of these are clearly slope of 1, 1 at the anchor point. So clearly all 3 of these lie on the same line. And this will become a bit clearer as we write this out. But that's essentially the idea we're going to follow. And then the answer is just going to be the item with the greatest value in our dictionary. So the first thing to do is take in our inputs. Now you can probably do this yourself, so I'm going to show you a pretty cool way, which hopefully you might learn something new doing this way. So we're going to we want a tuple. So we want a tuple of coordinates, essentially. We want a tuple of these 6 coordinates. So we're going to tuple it. We're going to map int input.split on the comma, and we're going to do that for I in range int input. So what we're doing is, for as many times as the very first number that's inputting, so it's 6 in this example, we're going to repeat this code in our list comprehension. And this code Well, we can split it down. So look at the map first. So the map will take in the input, which is a single line, split it on the comma. So now we have a list where the first element is the x coordinate and the second element is the y coordinate. And the map command basically runs the function you give it, which is the first parameter, on the list that you give it, which is the second parameter. So it runs this function on every element in the list. So it will turn each of these string numbers into actual integer numbers. And that's what the map does. And since the final format that we want our coordinates to be in is a tuple, we just kind of wrap all of that around with a tuple command. So that's kind of the input. So this basically just gives us a list of tuples where each tuple is a line of the coordinate input. So a coordinate of a star. Okay, now let's create that dictionary that stores everything for us. So dictionary is going to be, let's call it combs for combinations. Because it covers every combination of the anchor point and the slope. So now let's go through every anchor point. So for anchor in stars, what do we want to do for every anchor point? Well, we want to go through every other star. So let's say for other star in stars, we now want to do something. Except that we want to ensure that we don't ever hit the anchor point and the other star together. So let's check for that. So let's say if anchor equals other star, well, then the slope is obviously not going to really exist, right? Because the other star exists on the anchor point if they're the same thing. So we can just kind of continue that. And we know this will work just fine because if you go to the constraints, it says that all star coordinates are distinct. No two stars will share the same coordinates. So that means if this does share the same coordinates, it means we are dealing with exactly the same star, which is the anchor point. And we don't want to deal with the same star. We want to deal with the other 5 stars. Okay, so once we have the other 5 stars, what do we want to actually do? The first thing is we want to calculate the slope between that other star and our anchor point. So what's the x slope going to be? The x slope is going to be the difference between the x coordinates of the other star and the anchor star. So the other star is going to be other star, and the x coordinate is the first thing in the tuple, minus the anchor point. The anchor point, again, the first thing in the tuple is the x coordinates. So this gives us the slope between both stars, the x slope at least. So now I want to do the same thing for the y slope. So we just change that variable name to the y slope, change these indexes that we reference the y coordinate. And now we need to do the thing that we mentioned earlier, which is, great, now we have the x and y slope. We want to compress them down as much as possible, right? If there is essentially a smaller way of representing the same slope, we can do it, right? The same thing we had up here, where this was a slope of 2, 2, and this was a slope of 1, 1. We could compress the 2, 2 down to a 1, 1, because they are functionally the same gradient or the same slope. And we need to do that because that would let us essentially use the same slope to refer to multiple stars regardless of how far away they are from our anchor. Because if you look at these two subtractions depend on essentially how far the other star is from our anchor point. And that's kind of not fair. Like, we shouldn't do that. They should not depend on how far away it is, because we only care about the slope, because the line is infinite in length. So to kind of compress that down into what we want, we can use this command in Python, the greatest common divisor. So we can import that from math. So from math, import GCD, stands for greatest common divisor. And the GCD does exactly what it says. It finds the greatest common divisor between two numbers. So the greatest common divisor between the x slope value and the y slope value will allow us to kind of compress this down. And let's call this divisor. And how does this allow us to compress it down? Well, because we now have the greatest common divisor between both the x and the y slopes, we can just divide the x and the y slopes by this greatest common divisor, and we'll still end up with an integer value, a whole number integer value that represents the exact same slope. You know, it's like if you have a gradient of like 1 over 2, that's exactly the same thing as a gradient of 2 over 4. Like 1 over 2 and 2 over 4 are the same number. You just doubled it. And so you can find the greatest common divisor, which is 2, between 2 and 4, divide both by 2, and you get back down to 1 over 2. So that's a very similar idea of what we're doing here. So let's do that now. So let's say the new x slope is going to be equal to itself, but integer division by divisor, and the same thing for the y slope. So now we have the compressed x and y slopes. Now we can actually add this to coms. So coms, again, is a dictionary which contains a unique line. So each item is a unique line. And the line is defined by the anchor point, the x slope, and the y slope. These are everything you need to define a unique line. And what we're going to do with this, well, we're going to add 1 to this value, because it just means that we've the other star that we've just gone through well, this line passes through the other star variable. And so we're going to add 1 to commas by saying this combination of anchor and slope goes through this star. And so we can keep doing this, and then slowly some of these combinations will have numbers that are bigger and bigger and bigger. So for example, maybe this combination of anchor and slope goes through 4 stars, and we keep adding 1, so we kind of keep track of that. Now, a problem you may notice, or a couple of problems there are actually with this code. The first problem is you can't just add 1 to an item that doesn't exist in a dictionary. Right, so if this item doesn't exist, it's going to give us an error. And we can probably do a quick submit, and it's going to give us a runtime error. Yeah, runtime error. So how do we kind of account for that? So there's this really cool command in Python. You can import from collections. You can import the default dict command. The default dict command is a different way of defining a dictionary. So instead of using the symbols, you can just use the words default dict, and within the brackets of default dict, you have whatever default value you want. So if you want a default empty list, you have list. If you want a default empty string, you have string. If you want a default empty number, which is 0, you put integer. So that way we just start off with zeros, right? So the default value for every item in this dictionary is going to be 0. And that's what this accounts for, basically, because we're saying if we decide to add 1 to a key that doesn't yet exist in our dictionary, well, default dict is going to create the key and assign it to 0 by default. Lovely, and that's pretty much done. So at the end of our code, we can just print off the maximum value in our dictionary. So that's going to be max of comms.values. Now, there are going to be a couple of issues with this. And firstly, I don't think it's actually going to work. It's not going to work because this value, like the value at this key does not include the anchor point itself, right? Because if you recall up here, we've excluded the anchor point from all of these calculations. So the anchor point itself obviously lies on that line, but we haven't added that yet because the default dictionary goes to a 0 as opposed to a 1. And so we need to very final answer to account for the fact that the anchor point at that key actually goes through the line. And I believe this should actually get us the points. Yeah, so if you just want 10 points, and then I guess go away now. But if you want to kind of look into the problem a bit more and kind of look at a couple of interesting things, then stay along. So a couple of things. Firstly, GCD. The way this is implemented in Python means that the first variable you put in here cannot be a 0. It cannot be a 0. And that's essentially the whole purpose of this, right? So if we were to remove those 2 lines, just like that, and submit the code, we're now going to run into a runtime error. And the runtime error exists because this is going to be a 0. And you cannot have a 0 in your GCD, your first GCD parameter, because that means the way Python implements GCD is it means that they're going to divide by 0. You can't do division by 0 in maths. So that's why we have to have this. And the reason this was 0 is because if your other star is exactly the same as your anchor star, then your x slope and your y slope are both going to be 0, right? Because the coordinates are identical. So the result of that's going to be 0, and the result of that's going to be 0, and therefore that's going to be 0, and that's going to be 0. And you can never have that to be 0. You can have the second one to be 0, so that should still work. Now, a couple of points about how this works and why there possibly shouldn't work in a couple of cases. So if you have a vertical line, this shouldn't work. But fortunately, none of the 10 test cases have a vertical line. Like if the solution is a vertical line that hits maybe 7 stars, if that's the solution, our code will break. Because a vertical line will mean that the x slope is 0. Because like it's vertical, so the x does not change. So x will be 0, and therefore this will be 0. And we hit the same problem as we had before. So if you really wanted to care for that, account for that, which you would need to do if you perhaps didn't get 10 out of 10, but in this case we do, you'd essentially need to do something like if x slope is equal to 0, then you kind of ignore all of this divisor nonsense, and you can essentially just do this, but the value you put in your x slope, what we're going to say is, well, the value we put in our y slope, we're going to say is infinity. So, and then we have an else over here, like that. And I believe this should still work on the current code, because we never actually hit this case. And so yeah, we still get 10 out of 10 because you never actually hit the vertical line case. But if we do, this is how you handle it. We wouldn't call GCD because that would break the program, and we'd instead just kind of set our own custom X and Y values. And I mean, you can kind of set this to a 1 if you want as well, right? Like if we at this point we have isolated the vertical line, we can set this to whatever we want. Like we set that to like that number. As long as it's consistent, like that can be whatever we want. But we can set it to inf to kind of represent the fact that we have an infinite y slope and like a 0 x slope. So yeah, that's kind of one mathematically robust way that you would code this if you're a true pure mathematician, or if you just run into errors. And the second thing I wanted to point out is that this essentially, so if you have a point and you have a point to the top right of it and a point to the bottom left of it, well, they may lie on the same slope. Like those 3 points may all lie on the same slope. But because one is kind of below and one's above, your x and y slope values are different because they may be negative as opposed to positive. And that would cause issues. Here it doesn't. And here it doesn't because we're doing a brute force solution. We're doing a brute force because essentially this would not work if you decide to use the anchor point. So say I had a line that had 3 points. That's a line that was like this, you had 3 points, and your anchor point was the center point. This solution would not work because the point that's above it would have a different slope to the point that's below it, just based off the way we're calculating things. Now the reason this works in our code is because we brute force every single star as the anchor point. So even if the middle star anchor point fails, well, we can still use the bottom star as the anchor point, and that will work because the slope direction for the other 2 stars on this line is going to be the same. So I don't know if that made too much sense, but essentially the direction of your slope actually matters in our program. So it's not meant to matter, right? Like the direction of your slope shouldn't matter. Like whether it goes that way or that way, it's the same line. But our program doesn't account for that. But that doesn't matter because as long as we choose the very last or the very end star on our line, then the slope will always ever go in the same direction. Now to fix that, if you really care about trying to fix that, you can, and you can basically say that if x is smaller than 0, so if your slope kind of goes to the left, essentially, if your slope goes to the left, then let's just flip everything. So then x slope multiply itself by -1 to make it positive, and then y slope, you again just multiply it by -1 to kind of reverse it as well. So essentially we're making every left slope swap into a right slope, and this is what we're doing. You cannot make every left slope swap into a right slope and every up slope swap into a down slope. You can only swap one of the 2 x or y slopes. And I'm not going to get into that now. Like, you kind of have to play around or have experience with graphs and lines and whatever for that to kind of make sense. But yeah, this solution would be a much more mathematically robust way of doing it. But of course, we don't necessarily care about that. So I'm going to delete this code. And I hope you enjoyed that puzzle because I thought it was quite interesting. And it was a bit difficult, but play around with the code, get pen and paper, draw things, draw graphs, mess around, print stuff, whatever, until you understand it.